All right, Unit 3, Lesson 4, Factoring Polynomials. So why do we factor polynomial functions? Well, our whole point today, or when we factor, is to find roots of an equation. What are roots of an equation? Those are the places where the graph crosses the x-axis. We just spent Unit 2 on quadratics. We factored to find the roots so we could graph a little bit easier potentially. We're going to do the same thing with higher degree polynomials, cubics, quartics, anything to the 5th power, 6th power. We might be able to factor, and if we factor, that allows us to get an idea of what the graph is going to look like. So let's go ahead and jump in here and try to factor. So it says, solve each equation by factoring and list the x-intercepts. Not only are we going to list the x-intercepts, we're going to talk about the multiplicity of each one. Is it a single root, a double root, a triple root? We probably won't get more than that, but who knows? Okay, so let's look at example 1A and B. Example 1A and B, the key here is going to be to factor out the greatest common factor, the GCF. I don't know why, as people get older, they tend to forget about the greatest common factor. So we need to look. X cubed is divisible by x, 2x squared is divisible by x, and negative 15x is divisible by x. So therefore, I'm going to factor out that greatest common factor of x. I divide each of those terms by x, so I would end up with x squared plus 2x minus 15. Right? You can do a quick mental distribution to see if you distributed x times x squared, you'd get x cubed, x times 2x, you'd get 2x squared, x times negative 15, you get negative 15x. So yes, you have factored out the GCF correctly. From here, you can now factor this trinomial. You can use whatever system you have. I just like to jump right into factoring. What two numbers multiply to give me negative 15 but add to give me 2? Well, hopefully you're saying to yourself that's plus 5 minus 3. This is easier because there's no leading coefficient in front, right? The leading coefficient is just a 1. So I have factored fully 2x times x plus 5 times x minus 3. Now I need to get my x-intercepts or my zeros or my solutions. So either x equals 0 or x plus 5 equals 0 or x minus 3 equals 0, zero product property. You don't have to show that work. You could have also just written out the 3 zeros. All 3 of them are single roots, single roots, single roots. So we usually don't identify the multiplicity when it's a single root. We just list them. If it's more than a single root, then we usually put the dr or the tr or something else with it. Otherwise, it's assumed that it's just a single root. Okay, let's look at letter B. Our theme of example 1 is to look for our greatest common factor, our GCF. So 2x to the 5th and 18x cubed both are divisible by 2 and both are divisible by x cubed. So I'm going to factor out 2x cubed. What would I get as a result? Well, hopefully you are seeing that you would get x squared minus 9 because I would divide each of these factors by 2x cubed. Now I'm not done yet. I can continue to factor x squared minus 9 is the difference of squares. So I have two numbers that multiply to give me negative 9, that add to give me 0, and that is negative 3 and positive 3. Now, according to our fundamental theorem of algebra, if there is a cubic, that means we have 3 roots or 3 x-intercepts. Right? If it's a 5, that means we have 5 x-intercepts or 5 roots. So this right here accounts for 3 of them. Either x cubed equals 0, or x minus 3 equals 0, or x plus 3 equals 0. Because x cubed is equal to 0, well, what's the only number that you can multiply by itself 3 times to get 0? That's just 0. So 0 is a triple root. It accounts for 3 of those solutions or roots. Then another root, singular root, is 3, and a singular root is negative 3. I'm not going to put the SR there because it's assumed if we write nothing, then it's just a single root. All right, moving on. So our first strategy was to factor out the greatest common factor. Our second strategy that we're going to review, that you probably learned back in Algebra 1, is to factor by grouping. If we have 4 terms, then you want to look to try to factor by grouping. So usually we can group the first 2 and the last 2, but if that doesn't work, you can rearrange to see if rearranging is better. But in this case, we can factor the first 2. The first 2 have x squared in common, so I'm going to factor out the x squared and get x plus 3. The second 2 have the negative 6 in common. I'm going to factor out my negative 6 and get x plus 3. Remember, when you're factoring by grouping, these x plus 3's need to be identical or there's an issue and you can't continue. So now I can have my x plus 3 as my greatest common factor, and then x squared minus 6 is left over, and so this is my final answer if I'm going to factor, right? So that is factoring. Now how do I solve? I would continue to x plus 3 equals 0 or x squared minus 6 equals 0. Therefore x equals negative 3. Here I would get x squared equals 6. I have to take the square root of both sides. When you take the square root of both sides, I have 2 solutions. Remember, the fundamental theorem of algebra says if it's x to the 3rd power, we are going to have 3 solutions, or 3 roots, or 3 x-intercepts, however you want to think of it. X equals negative 3 is just 1. My other 2 are plus and minus root 6. So there are my 3 zeros. Okay, I would say pause here and try example 2 on your own. Try the grouping. You should be good at this. I know a lot of you do the method where you create the x, which is factoring by grouping. So pause and try this on your own and then check back. Okay, so letter A, you should have gotten zeros of 4, negative 4, and 3. How did I do that? Well, I grouped the first 2 and the last 2. I factored out an x squared to get x minus 3. I factored out negative 16 to get x minus 3. Then x squared minus 16 was the difference of squares, so I factored that into x minus 4x plus 4 to give me 3 zeros of positive 4, negative 4, and positive 3. For letter B, it was slightly more complicated. Not only were the numbers a little bit yuckier, but also your final answer, what happened there. So we've grouped the first two. The only thing they have in common was a 3 and an x squared, so I get 12x minus 5. Well, this is a hint as to what you might divide by, right? You could take 84 divided by 12. What do you get? You get 7. So factor out your 7. You get 7 times 12x minus 5. Awesome, they're identical. But then I get 3x squared plus 7 as a factor and 12x minus 5 as a factor. So 3x squared plus 7, we're going to set that equal to 0, but can you take a number that's positive, 3, multiply it by a square, which has to be positive, because when you square any number, you get a positive result, and add something to the already positive number and get 0? You didn't even need to do all this work. Hopefully you would have looked at this and said, wait a minute, that's not going to produce an answer, because I can't take a positive 3, multiply it by a positive squared number, add something to it, and get 0. So that resulted in no solution. So my only solution is 5/12. Now as we continue through this unit, we're going to figure out what that looks like graphically. We're going to kind of approximate. We're not really going to do much with it graphically other than approximate. So let's see as we continue through the unit what that looks like. Okay, so this brings us to why on earth have we used or learned about long division? So we've learned about long division to do problems like this next one. So if you have 4 terms here, x cubed plus 2x squared minus 5x minus 6, and that's part of your polynomial function, then you try to group because it's 4 terms. But if we tried to group, we're not going to get anywhere, right? If we tried to take out an x squared, we're going to get x plus 2. There's no way we can get this to become x plus 2, so we're stuck. So we can't factor by grouping, so what on earth are we going to do? Well, we must be given some other information. So here we're telling you if we divide, maybe we tell you that x plus 3 is a factor of p of x. That's probably what we do. And if we told you that it's a factor, then you can do long division. And you can say, okay, I'm going to take x cubed plus 2x squared minus 5x minus 6, and I'm going to divide it by x plus 3. If we tell you it's a factor, that means it divides into it evenly, and you should get a remainder of 0. So now I'm going to do my long division. You might want to pause. I would recommend you pause and do this on your own. I'm going to pause. I'm going to fill it out. So practice your long division. Pause now and try it on your own. Okay, so when you did your long division, you should have gotten your quotient to be x squared minus x minus 2 because x plus 3 was a factor, so you should have gotten 0 as your remainder. So what does this mean? That means if I took my denominator, which is x plus 3, and multiplied it by my quotient, I should get my p of x, right? So this thing here means that if I took my quotient and multiplied it by my denominator, then I would get my original polynomial function. So now I can just go ahead and continue to factor by taking this underlined portion and factoring by grouping. Oops, that's not what I wanted to do, sorry. And so what two numbers multiply to give me multiply to give me negative 2, but add to give me negative 1. Hopefully you're saying negative 2 plus 1. So this is my final answer. When it says to fully factor p of x, we would get p of x equals x plus 3 times x minus 2 times x plus 1. So this is the p of x fully factored. If we asked you to solve, then you would have set that equal to 0, and you would have gotten x equal negative 3, 2, and negative 1. So if you were to graph it, the graph would cross the x-axis at negative 3, positive 2, and negative 1. But it just says to fully factor, so this is my final result. All right, so here it says to solve this function completely given that x equals 2 is a root. So solve means to actually find your zeros. So when f of x equals 0, then what are your x-intercepts? So solve means actually set it equal to 0 and find the solutions where the graph is going to cross the x-axis. We already know it's going to cross the x-axis at 2 because that's a root. But what else can I do? Well, I might want to look to see if I can factor by grouping. I can't. That's not going to work. So I'm going to have to take this xz root, and I'm going to have to do long division to figure out the rest. So if x equals 2 is a root of the equation, then x minus 2 is a factor of the equation. And if x minus 2 is a factor of the equation, then I can do long division by taking x minus 2 and dividing it into x cubed plus 4x squared minus 3x minus 18. I will get my compressed polynomial, so I can continue to factor to find out what my 3 roots are. So here you should be able to pause. This is just like example 3, right? Except then we're going to go back and we're actually going to solve by setting those factors equal to 0 and getting the places where they're going to cross the x-axis. So do long division, see what you get, and then unpause and come back and see what's happening with me. All right, if you continued to the end, you should have gotten one of your roots was 2 and the other was -3, and that was a double root. So when you did your long division, did you get x squared plus 6x plus 9, right? Then that means your function equals x minus 2 times x squared plus 6x plus 9. X squared plus 6x plus 9, we can now factor that. What two numbers add to give you 6 but multiply to give you 9? Well, they're both positive. So 3 and 3, both positive, added to give us 6, multiplied to give us 9. And then we actually have to solve. So solve means set it equal to 0. So using our set this equal to 0, our zero product property, either x equals 2, x equals -3, or x equals -3. Therefore, -3 has a multiplicity of 2, or -3 is a double root. Okay, so what does it mean if the function has a root of 2, right? So if a function, like that function we just did, had a root of 2, so a root is a place where it crosses the x-axis, right? So this is another way of thinking about it. A root is also where it's going to cross the x-axis. It's an x-intercept, right? So this is saying it's an x-intercept. It's also, if you put it in function notation, it's saying f of 2 equals 0. This is an f, not a p, so I'm changing this to an f of 2 equals 0. It's also saying that x minus 2 is a factor, right? If f of a equals 0, then x minus a was a factor. We have that in the remainder theorem. So a comma 0. So all this stuff goes together, which is why we're doing all these little points on the star here. And finally, if you took the function and divided it by that factor, you should get a remainder of 0 because it's an x-intercept. If it's a factor, that means it divides into that function evenly, and you should have a remainder of 0. So that's kind of a summary of how all those vocabulary words and different things that we're doing go together. Okay, let's look at these final couple of examples. You might want to pause and do them on your own. I think you could probably do it on your own. Number 5, it says, consider the polynomial. Use long division to fully factor g of x, given that we have one of the roots. So we know it goes through -3, 0. If it goes through -3, 0, remember that star, that means x plus 3, is a factor. And so we're going to use long division because we can't factor by grouping. So we have to use long division, and go ahead and do that long division and then try to sketch your graph and then come back with me and compare it with my answer here shortly. Okay, we did our long division here. You should have gotten your long division and gotten x plus 3 times 2x squared plus 5x plus 3 when you did your long division with a remainder of 0, but 2x squared plus 5x plus 3 can be continued to be factored. However, whatever method you use to do that factoring, you should have gotten 2x plus 3 times x plus 1, which means my 3 roots are -3, -3 halves, and -1. So the question now is, how do I sketch that graph? Well, I have a 0 at -3, I have a 0 at -3 halves, and I have a 0 at -1. I have a y-intercept of 9, right? How do I know I have a y-intercept at 9? Well, if I put in a 0, a 0, and a 0, I'm just going to be left with 9. So I have a y-intercept of 9. It's my x-axis, my y-axis. And the last thing I need to do is look at my end behavior, right? This was an odd function. It's 2x to the third power, which means my end behaviors need to be opposite. One needs to be increasing, one needs to be decreasing. If it has a positive leading coefficient, then we always start by going uphill, right? Which means at the end it's going down and we end by going uphill. So it's going to go through, go through, go through, go through. Sorry, that's a little bit not going through very accurately. I'll just make those points a little bigger. Apologies. But that's what your graph should look like. How high up this goes and how far down this goes, it doesn't really matter. We're not looking at those values, so don't worry about that. But your end behaviors are really important. It needs to end going up because it has a positive leading coefficient. It needs to begin by going up, right? So in other words, as you go to the left, it's going to go down. So that's it for example 5. Example 6, let's see. So example 6, I would say use the strategies we just did from before and try the same process and see how you do. Compare your answer with me when you're done. All right, this final problem had one little wrinkle in the answer. So when you did your long division, did you get 2x cubed plus 2x squared plus 3x plus 3? Hopefully you did, and then you took this part on a little side note and you said, okay, I need to factor that. It's 4 terms, so I can factor by grouping. So I factored by grouping and I got this, which means now my polynomial function of f of x is equal to 2x minus 3 times 2x squared plus 3 times x plus 1. Then I have to use my zero product property because I'm trying to solve, which means I'm trying to find the x-intercepts or the places where the graph is going to cross the x-axis. So I set it equal to 0. When I set it equal to 0, you can go straight from these to answers, right? 2x minus 3 is going to be x equals 3 halves. X plus 1 is going to be x equals negative 1. But what happened here with this positive coefficient multiplied by x squared added to 3, when you have this, you can't get it equal to 0. You can't take a positive number, add a positive number to it, and then just have this number squared. It's all going to be positive. So it's not possible to make that 0. So I only have 2 zeros. They're at 2 real zeros, excuse me. These are going to be imaginary. You'll learn more about that next year in pre-calculus, but we have 2 real zeros. They're at 3 halves and negative 1. So I put my roots on the graph, negative 3 halves and positive 1. Oh dear, I reversed that. Apologies. So this is gone. This is supposed to be positive 1, and this is supposed to be positive 3 halves. So sorry about that. Just ignore these original roots. Whoops. Then I would continue. I have a y-intercept of negative 9. If I put in 0, 0, and 0, I'm just going to get a y-intercept of negative 9. So here is what I have. Then the last thing I need to do is look at my end behaviors. This is an even function. That means my end behaviors both need to be opening up and up, or they need to be opening down and down. If it's a positive leading coefficient, then I need to have up and up at the ends. So I come down, I have all single roots. It comes through there, goes through here, goes through 3 halves. Doesn't really look like a quartic, but that's okay. You could leave it like that. You could come down, you could put a little wrinkle in your graph. You could come down and put a wrinkle in your graph here. You could come down, put a wrinkle in your graph wherever you want, or you don't need to put a wrinkle. There's an infinite amount of ways that you could draw this quartic graph. The important thing is that it goes through negative 1 on the x-axis, negative 9 on the y-axis, and positive 3 halves on the x-axis, and that it's increasing as x goes to negative infinity. It's increasing as x goes to positive infinity. It's also increasing. So your end behaviors here are really important. All right, hopefully that made some sense. If not, you definitely need to reach out to your teacher and ask questions because we are here to help you. Bye.